today is related to multiple self-cracking and debonding for thin thermal coatings. And the main motivation for these studies are related to the advanced material must perform under complex severe external action like thermal, chemical, dynamical impacts, cyclic loading. And in order to perform well in this very complex loading condition, we have to combine different materials such as composite material, for instance, ceramic metal composite. And in this part, we can see there are layers of metals and ceramic materials, and the complex failure mechanisms are really related to the bonding and strain localization, fracture kinking, and many other complex phenomena that has to be taken into account. And in order to model this kind of problems, we typically have two main failure modes. One is the diffusing elastic strain or formation of localized failure in the bulk materials, which may bring to localized fracture. The other is the equation along the weak surface, which typically connect the different parts of the material. The common approach can be based on damage mechanics, but it has to be used in a different way in order to have these two different effects. One is the intralaminar diffuse damage, and this can be faced with continuum damage mechanics, but with some special rules in order to keep the problem well posed. And the interlaminar damage are typically employed by interface damage mechanics. And so we have a continuum problem where elastic damage in a quasi-brittle material develop. And as we said before, this is a formation and propagation of microvoids, micro-rupture, diffusing elastic strain up to the maximum strength, following by softening branch. And when softening branch starts, we have to take into account the induced localization feature. Concerning, and this can be found with the non-local damage model, as presented many years ago as a general problem. Concerning the surface, we can introduce interface model in a multi-scale approach, and the main feature of this model has to be the capacity to model adhesion between bodies and fracture propagation along known surface, so then frictional effect between rough surface and sliding contact, and also once the crack is opened, the unilateral contact between surfaces in a complex loading pattern. So the problem can be set in a very rigorous thermodynamic way, leaving this is the body, so we can distinguish internal back energy density for unit volume in the bulk parts and internal interface energy along interfaces. Of course, for each of these parts, we need to introduce the related state variable and internal variable in order to model the problem. Here is briefly considered. So if we have the total internal energy of the body, we have something that has to be integrated along the bulk volume and the other part along the interfaces. So this is a standard derivation of thermodynamics. We can apply principle of virtual work of the divergence theorem, and then we arrive to this part, which is still related to the total volume of the body. Then we have to localize the law with reference to points which are inside the domain or with points which are on the surface. And when we do this localization, we arrive to define point-wise first principle in this part, and this is also related to thermal flow. And at the interfaces, where jump in the displacement, it looks can be considered. Related to the second principle, when we use the bulk part, we have possibly delocalization, and in order to preserve a well-positive problem, we have introduced a non-local approach, which which means energy exchange between points. So it's not a material, a simple material that we are considering. And then the second principle, once again, is written with refer to the active zone. But when it goes in a local form, we have to introduce some special terms, which is called non-locality residual function, which takes into account energy exchanges between neighbor particles. And of course, because the system is closed, we introduce also an insulation, a general insulation condition. The Helmholtz free energy is here reported. It's still for the part of the problem. And we have the strain energy. This is the composition in the principal direction space in order to have the monolateral behavior of quasi-brittle materials, and also an hardening rule, the internal variable here reported. The state law can be derived using standard procedure of continuum thermodynamics, and we have the constitutive law in terms of stress and strain in the principal direction, the energy release rate here reported, and the internal variable which drive the hardening behavior. The important things in the non-local approach, it is that also the energy release rate has to be computed following a space averaging. And dissipation comes in this way, and then we have the non-local damage flows here reported. So what we have here is in the activation damage function, there is a value of the energy release rate, which is not pointwise, but it's an average in the active zone. So the damage hardening law that was shown before is something like this, and was proposed by Comi and Perego, and has the capacity to go to infinity, keeping finite the area, the integral, which means finite fracture energy. Concerning the interface, we have to model adhesion between bodies, friction between rough surface, and unilateral contact. We can approach on this feature using an integrated interface approach, in which all these features are considered, and also we can model a smooth transition between cohesive and frictional behavior. So the methodology implied is generalized damage mechanics and thermodynamics with internal variables. Here we have the main feature of the model. So we have the damage variable, which is considered not just for describing the stiffness degradation, but it's also a geometrical measure of the fraction of the sound area. So if we take a little piece of the process zone, we can obtain two fractions of this part. One is the sound fraction, the other one is the cohesive fraction. And with these two fractions, we have also, from a static point of view, two different traction vectors. So this is, as we said before, is a real multi-scale approach, because this is the structural level, at the structural scale, the situation. This is the cohesive part, this is the sound part, this is the process zone. And taking a point of the cohesive zone, we have again two parts, two fractions, here reproduced. So the strain decomposition is done for the two different parts. The one is the sound, the other the graphic fraction, where we have different components that are able to describe the friction, the cohesion, and also the latency of the structure. All considered together. Looking into the statics, we have the composition of the traction vector, and the traction vector has two components related to the sound fraction and to the cracked fraction. Again, we can use thermodynamics approach here, reported the state law, but the most interesting things in this model of interface is that the energy release rate has not just the usual term, but there is another terms here with a minus, and this represents the energy stored at micro level, as this energy is not available for damage propagation. It can trap in the material. Then the activation function, damage activation, the frictional activation function, and because of the latency effect, a potential function. These are in the form of the molecular expression. The formulation is completed by the flow rules here reported. These two models have been implemented in an open source finite element codes, and as we see, the non-local effects are considered in this region. This is an interaction region. The element has to be close, and the diameter of this influence zone is something related to the internal length of the material. Now, going to the specific problem, the thermal barrier is reported a graph that shows the effect. So if we consider a turbine blade, which is a superalloy substrate, which is the part considered to carry the loading and the mechanical effect. And because of the very high temperature on the other side, we need to have this top, this coating, which is typically a ceramic material, and then a part that make possible the adhesion between these two parts. Okay, this was the first application of this coating. So, as we see, the problem is really complex. Many effects are involved in this problem. So, this the superalloy, which is awfully elastic, or this is the structure, the real structural part, and then there is the top coat, and the effect that has to be considered are of mechanical nature, because there are, of course, mechanical attraction, thermomechanical, because of the high temperature transition, and the thermochemical, because also chemical effects are considered. The most important of that is oxidation along this interface, which is a proper zone where delamination fracture can develop. So it's a multifunctional coated solution here reported. Here we see what is expected from an experimental point of view. So this is a specimen of 30 millimeter long in a 3-point bending test. And as we see, the typical failure phenomena is the formation of vertical fracture. These are localized here. There is the formation of the first one, and then a certain number. This fracture can go through the thickness of the coating, then reach the bonding coating on the substrate, and then it's almost impossible to still propagate in the superalloy, and then delamination may start. So the point is, these are the formation of these cracks, which are the length between one and the other can be computed, and then this is another experiment of the same time, maybe more complex. It's a 4-point, but the situation is more or less the same. And we can have a detail of the formation of these vertical cracks, and then the delamination along the substrate and the coating. So the problem that we analyze for this kind of situation is here reported. We have an element with these 3 parts, and then an interface which is posted here. We have done 2 analyses, because they are really 2 different kind of failure mechanisms. One with a relative thin coating, and the other one with a thicker one. And this is an impure bending state. This is the discretization that we have adopted. In the red line is the interface, which keep inside the information about the possible delamination between the 2 materials. And going to the material property, these are taken from the literature related to this problem. And so local damage is this one, and the cohesive is bilinear. And these are the finite element results for the thinner. So it starts uniform, then the first localization starts. This is just the thermal coating. Then the other are produced, and it goes like that. And then other other fractures start from the bottom, from the delaminate part, and this is the fragmentation, the spallation of the part. The second analysis is the thicker one, and the situation is more complex. Again, the formation of this large zone, but then, because of the thickness, we have inclined fracture that start from the bottom, and in this case, the spallation of this part is more pronounced, as is described by the experimenter. So, as a conclusion, we have to consider that this problem has the two main features: the fact that the thicker the coating is, the better the protection, the thermal insulation is. But in this case, we have some problem in mechanical point of view. Of course, the problem would require a more sophisticated multi-physical model which takes into account all the other effects that in this preliminary phase has not been considered, as a temperature and a chemical effect. Thanks for the attention.